Welcome to Gabversity, where facts took your feelings and locked them out of the house, and your feelings starved to death. So let's do it. This is going to get very boring for you guys. And if it is boring, I apologize. But that's life. It's only going to be mathematics this time. Let's go. Alrighty. Let us begin. I don't know how this is going to look. This may or may not flip around. We shall see how we go. I will do my best to... Amy Lorraine, welcome back, my dear. Where are my lecture notes? Here are my lecture notes. So, this... Yay! Hello. Here is this... I'm really struggling to figure out how to do this. Here is the standard Schrodinger equation. In one dimension, we have psi of xt. And this equals, here's the standard equation, a e to the minus, where am I here? I can't see what I'm doing. Should be crap. I can't see what the hell I'm doing. Look how quickly we lose people because I don't know what I'm doing. Damn it. It should be AMX. Should be the mass. Where am I? Yeah, let's just do that. Okay, so to the minus a m x squared over h. We're doing our best, my friends. We're trying. And then e to the minus... Oh, they're using a instead of omega. That's what it is. Okay, let's just do that. E to the minus I at. There it is. Math, rest in peace. This is the Schrodinger equation, the general form. Now, if it is of that form, then how do we discover A? Well, all we have to do is normalize. And if you don't know what I'm talking about, you're better off go to see the last scopes that I did. But we are now going to normalize. And to do that, we are going to say, let's see if I can do this, integral. This is so uncomfortable. A equals a vector. Ooh, good question. In many cases, yes. In this case, it is simply a number which helps define the wave function. So it's a scalar multiple from the... Okay, to infinity of the absolute value of the wave function squared dx equals 1. This is normalizing. What this means is that we are setting, as we said before, we are setting the location between negative infinity and infinity where the absolute value is going to be 1. In other words, we are going to find the particle in this wave function. 1 is 100%. All right, so now we're going to chuck in the equation. We're going to, this here is that equation. And if I'm going to square it, then I'm just going to chuck in a 2 there, absolute values. Yeah, bingo. All right. So that equals 1. And that, this is so freaking difficult. I don't know how I'm doing this. All right, let's see. Which implies, I'm like looking around the phone. All right. So the absolute value of a squared, so we've got the integral of minus infinity to infinity, right, of the absolute value of a squared. Man, you guys are very tolerant people, I tell you. E to the minus, and because we're squaring it, it is now 2 of all of that. So it'll be 2a m x squared over h. It should be h bar, actually. I don't know why it just says h. It should be h bar. And then this squared becomes equal to 1, because if anyone knows, when you multiply a complex number by its conjugate, that's squaring it, you get 1. If anyone remembers, here is the complex field, just to give you a quick of an update. Here's the complex field. This is the I direction, and this is the real direction. Conscious factor animates the pen. All right, that's the real number. Ah, good memory. And here is the imaginary, right? So we have an imaginary number up here. You know, this might be an imaginary number. It's when we square it, we're squaring it by, are you doing integration? Oh, good question. Yes, we shall be doing some integration. And here is the complex conjugate. So this, let's just call this, you know, the number C. This is C star, right? And when you square something, that means you're timesing it that by that, and you're going to get 1 in this case. You're a very smart dude. I'm good at copying. How's that? I'm just copying lecture notes. All right. Are we proving multiple dimensions? Ooh, multiple dimensions have already been proven many times. And that's a very good question. This part here is elementary, yes. This would be like advanced high school maths. And this here was probably like second year university calculus. So it's not too advanced, but if you know some maths, it's not too advanced, yeah. Alrighty, so we have that. Now we're going to integrate this. Well, we can take the A outside, right? And we're saying that this equals 1. It's delayed in the phone. Lol, you knew it. Amazing, Antario. That's why, my friend, you are amazing. Is that minus AM 1 over H? Oh, good question, sorry. AM X squared over H bar. The math for the 9th dimension. You believe in multiverse? I'm not a believer in general of things. I'm more, let's just see what the evidence shows, and we can maybe be 95% convinced. Okay, so the next line, my high school app. Yeah, that's right. All right. You clearly you're doing some advanced calculus at school. What a beast. So we can take the A outside. It is, if you're doing, like I did a maths degree, and if you've, this is why my absolute value joke. You know how long it took me to get your joke? I just got it. That's so bad. I'm going to have to go watch it again so I can actually feel a bit smarter. Too funny. All right, so we're going to take that outside because it's just a constant. Yeah, if you've done university level maths, this is a bit of a joke, like in terms of maths. But if you've done high school maths, then it's it's okay, because we're still dealing in abelian matrices. If anyone's done pure mathematics, you'll realize this whole thing is nothing. Just being silly. Oh, it's always fun. There is nothing better in life than being silly. Until you get kicked out of your scholarship, which really pissed me off. Minus infinity to infinity. Without using imaginary factors. Good question. The imaginary factors actually die right now because we're squaring it. By squaring it, the imaginary factors disappear. But in the quantum state, the imaginary factor's there. So clearly there is something to do with parallel universes hidden within quantum fields or quantum mechanics. Something's going on there anyway, or some sort of extra dimension we can't see. So we're going to integrate this, right? And when we integrate that with respect to x, we are going, what's the integral of that? 2am x squared, that'll be that over 3, isn't it? Yeah. Is this quantum mechanics? Can it die if it's imaginary? I don't know. What does the absolute of a represent within the function? Ah, another good question. This is awesome. I didn't know so many people were interested in maths. That's so cool. All right, so this a, you could sort of imagine it to be the amplitude of the wave function. What brings actuality from potentiality? Observation. It's jogging your memory. Wow, go Lilibel. Impressive. So let's integrate this, which I think, what's the integral of that? We're only integrating with respect to x. I forgot to put the dx, sorry. Oh, you're always welcome, Soul Traveler. This is nothing without you guys, my friends. So minus 2am x squared, let's integrate that. That's going to be that over 3, I'm pretty sure. So that'll be minus 2 over 3 am x. Hold on, have I done, I think I've done something wrong. Hold on a sec. Let me simplify this. So, because I always forget how to do this. E to the integral of e to the 2x, derivative of e to the 2x will be 2 e to the 2x. So the integral is that over that. Ah, crap. Okay, I don't know what I've done. What have I done wrong? 2ai n x squared. Ah, okay, because it's e to the x squared. All right, so I gotcha. Minus 213. What a beast. What a beast. Because if we derive that, let's say, let's try it. Let's Schrodinger's cat. Minus 2 over 3 amx squared, this is not coming out very well, over h bar, that should be cubed. Let's just have a look. They lied to you. Dx e to the minus 2amx squared over h bar. Minus 2 became a plus 2. This is right. You are exactly correct. So if, let's just test it the other way. That can't be right. First in the course here. This is bringing back some memories for me too. So if I derive, I've got to test it the other way. I've got to derive this first. So deriving that will be minus 4 am x over h bar e to the minus 2a m x squared over h bar. That would be the derivative of that. And then to integrate it, you'd have to have an x term out here. Yeah, excluding imaginary factor, because what happens is up here, what we're doing is normalizing. We actually square the function. So we're squaring all of this. So to square all of this, this part is you multiply it by its complex conjugate, which is here, and you end up getting 1. So that actually disappears. Yep, perfect. I know it's annoying. I get the feeling. So here we can see that I'm going to use the table of integration at the moment because I don't want this to become an integration by parts lecture. But if you see here, the minus 4 came from where? What I've done is I've derived this as a test. I've just derived this. I haven't integrated it. By deriving this, you get this, because basically it is the derivative of this which goes here, and there's an x term in there, which means that if you wanted to integrate this term, you need an x out here, and there isn't one. There's no x out here. So I'm just going to use the table of integration. So I'm going to skip all of this, because what I mean, let me show you what I mean. Does anyone know the integral of e to the x squared dx? Integral of e to the x squared dx. Back math to solve. Exactly, back math to solve. Soul traveler, man. You are traveling very quickly. E to the x squared, the integral of this cannot be done unless you use a series. So you can say n equals 0 to infinity, right? And it'll be some sort of equation. It'll be, nx to the n minus 1, blah, 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 blah. It'll be, you got to convert that into an infinite sum and then integrate it, right? But I'm going to save that because I don't want to teach infinite series here. That's more of a pure maths course. So what I'm going to do is I'm going to turn the page and I'm going to use table integration because this is physics, not mathematics. Right, let me start again. We're wanting to normalize the equation. So let's start again so people aren't too confused. Integral of minus infinity to infinity of psi absolute value squared dx equals 1. That's the first thing we're going to do. And the next thing we're going to do, this is so hard to hold, man. If I try to look at the thing, the phone goes out of the way. All right, so the next thing we've got here, we're going to put the equation in there, which equals minus infinity to infinity of absolute value of a squared e to the minus 2a mx squared over h bar, and then the other part squares out and becomes a 1. So that's what we're up to, and that implies that equals 1. Okay, so then the next one is, if we use our table of integration, we know that the integral absolute values there. Absolutely, my dear. I should have picked that up. I'm a slow bugger sometimes. All right, which implies that a absolute value of a squared pi h. Thank you. That's a very kind way of looking at it. I'd say focused. Over 2 times mass times a. And a, you can call a, if you want, at the moment, the angular momentum of the particle, but it's not really what it is, but it's analogous to that. Okay, so that equals 1. which is great, because now all we have to do is say that this implies that A equals 2 by the mass times A over pi h, all to the power of a quarter, which is, your intelligence never ceases to amaze me, Gab. I'm just scribbling letters. They just make me look smart. I'm not really that smart. Well, I could be that smart. You don't know. All right. So, there you go. So now we know what A is. A equals this. Yeah? That's pretty cool that you can see that. So now we can go back to the original equation. Right? So if you guys remember, the original equation for the, like, this is what Schrodinger found out. He found out that every quantum wave, purest language is math, absolutely, it is the language of the universe. What he said was that all quantum waves, right, and this is only one dimension of space, one dimension of time, all of them come in the form of this, A by e to the minus. Did he ever find out what life is, though? Probably not. My dear, that's where you come in and make your beautiful music, because life is all about that. A mx squared over h bar. I try to. And then e to the minus I, it should be at, am I right? Yes, I'm right. Okay, so that is, music is a mathematical, absolutely. Very, very true. But now we know that A, we figured out, is this. So therefore, we can say that phi of xt, which is the wave function again in one spatial dimension, one time dimension, equals 2ma over pi h bar, all to the quarter. All right, we've just put this in instead of A, right? That's all we've done, right? E to the minus mx squared over h bar, e to the minus I at. So all we've done here is basically, now you, I forget who it was, that other guy, that gentleman. Let me see if he's still here. I'll recognize his icon. I think it was Soul Traveler. I can't see. It might have been Soul Traveler. I'm not sure. But someone said, what was A? Was it? This is A. So A is 2 times the mass by this little number A, which we're going to call angular momentum for now. Some people call it omega. Me. And over pi h bar. And h bar, if you guys remember, is basically the size of the smallest possible pixel that exists in our universe, as we know. Nothing is smaller than that, right? I asked if it meant vector. Yes, you did. To the power of a quarter. So that's what A is, right? Please open your microwave. I think you are way too quick for me. E minus mass by x squared. Now x is the distance, right? Over h bar. And then e to the minus I. I is the complex number, square root of -1, by the, let's call it angular velocity for now, and time. So if we have all of these, we could solve for the time. Or if we have the time, we could solve for the distance, right? And these distances are average. So that's the wave function. This shows you all the possible locations of x given time. There it is, right there. Now let's look at the spatial component of the function. This is the spatial component of the function. Love, hey mum, this is beauty in the world. You guys are awesome, man. So this here, this section, just that is the spatial dimension. All right? Spatial dimension of the component. And this is the time dimension of the component. So this is 2-dimensional. But this x is only 1 dimension in space. So once we get 3 dimensions, that's going to become a 3-dimensional vector, coming back to Amy. Once this becomes a vector, this will become a vector. At the moment, it's only a scalar, right? But you're exactly right. That'll become a vector. Haha, you just got here. Welcome back, Justin. That's all right. Okay, this will become a vector because this is a vector once we do three-dimensional equations, plus time will be four-dimensional. Not already three, not in this equation. In this equation, we're only using one dimension. So we're pretending that we're a cartoon moving backwards and forwards. And that's it. So one particle sort of moving backwards and forwards, you know? So let's just say I have like a whirl and I have the particle, yeah, it's sort of going like that and then like that. But later on, yes, we're gonna, in the later mathematics, we're gonna do this. And then it's weird doing this through Periscope because it's delayed as I'm drawing it. So I'm like, why is my hand back over there? You know, we're gonna do this. You know what I mean? And then the particle is going to go everywhere. And then instead of having X, we're going to have R. So this implies that X goes to R. Right? Multiple mathematical solutions. It does, but we only take the absolute value. That's another good question, man. Jeez. Your mind is like full-blown there. That's great. So, yes, it does, but that's why we take the absolute value. But I forgot. That's a joke in itself. All right. So later on, once we swap that with R, that's going to be 3 dimensions plus time, which is the fourth, which brings us into the Einsteinian general relativity where space and time were connected. All right, cool. So next, the time-independent Schrodinger equation in 1 dimension. Now I'm going to show you that. Okay. Time-independent Schrodinger equation in 1 dimension. Here we go, which is minus h bar squared over 2m. All right. And then we have the second derivative, d2 psi of x. All right. This is the partial equation, dx squared. All right. So this is the Planck's constant squared, negative of that, and that's called the reduced Planck's constant. It's the Planck constant over 2 pi, right? Divided by 2 times the mass, multiplied by the second derivative of the wave function, only the spatial section, the one that we just looked at. So it's a lowercase psi of x. So it's not, as I told you, that here, that's psi of xt. But psi of x is only that section, the part, the small part, not including this, right? So just this part here. All right, so here, excluding time, exactly right. So this is basically the spatial possibilities independent of time itself. Exactly. So you're taking a slice out of the 4th dimension. You're reducing the dimension, right? Yeah, that's all right. Plus the potential energy of X, which we call V of X. All right, and that's the potential energy of the particle. Whenever you see X by itself, then that's the particle location, right? So of that particle, multiplied by psi of X, which is once again that same wave. So that's the second derivative of this wave, right? Equals, okay, energy, right, multiplied by psi of x, which is the wave function space only, right? So there it is, right there. Okay, bingo. So once again, we've got the reduced Planck's constant minus that all squared over 2m, and we always have the Planck's constant, of course, because that's the size of the pixels of this universe, this one at least anyway. And here we have what? We have the second derivative of the spatial equation. Holy cow, you're gifted. That could be a dirty joke, but thank you, I appreciate that. All right, potential of x multiplied by psi of x equals, right, energy multiplied by psi of x, which is very interesting. So if you get the energy and you multiply it by psi of x, you get exactly this, right? He's explaining the delay. Yes, the delay. The delay. Okay, so how do we find the energy? The energy can also be found from the time equation. So now I'm going to... Oh, bloody hell. Keep losing my charger. Man, Periscope sucks more battery than a wombat sucks milk out of its mother's teat. All right, so the next one. Does this Orstek account equate the apparent frequency of the wave? Ooh, look at you. What is it with you guys, man? I feel like my IQ has gone up to 1 million when all you guys are there together. Yes, it does take into account the frequency, but only in spatial direction. So it doesn't take into account time. And it's also not good for, yeah, very smart. It's awesome. It doesn't take into account a particle's moving at relativistic speeds when time starts to get messed up and so space gets squashed up. So it's a very simplistic version, and that's what we're starting with. And we're going to get there. We will get there in the next couple of months. If you can watch every single video, by the end of it, you'll be doing quantum relativity. All right, so now the energy can be found from the time equation. Here we go. So energy, again, right? Don't tell anyone though. Sorry, let me get where I was. What the hell? Okay, yeah. So energy, and then we're going to call this, let's just call this E of t. All right, so this is the function over time. That by that equals, I'm actually learning this with you guys, by the way. IH bar multiplied by d that dt. D of this thing, dt. Texas, this is an amazing scope. Well, Jason, thank you. You've made my day. I wouldn't do this if you guys didn't think that, so that's awesome. All right, so therefore, here we go. And as I said, the time component was here. So what I just drew for you is, this is the time component, right? We said in the whole equation, this was the spatial component, and here is the time component, right? So let me actually draw that. So that is time component. And this section is the space component. King Hor and Amy. Sounds like a good match. All right, so we have here the engineering calculus, never physics I'm observing. Engineering calculus, oh, well, it'll probably overlap quite a fair bit with this. So that's the space and that's the time dimension. So we know that the energy is related to this part as well. And that's going to help us solve for energy in the future when we have missing information. So once again, we know that it equals that. But it also, right, we know that E of t equals, as I just showed you on the other page, it is e to the minus iat. Now, some people use omega in place of a, which looks like a curved w, but whatever, right? You might get confused initially. All right? And so therefore, right, therefore, E equals I'm married with 8 kids. I'll take it as a compliment. Can mathematics prove God? That's a very good question. That's actually a very good question. So when I was doing abstract mathematics at uni, it showed that there were rules that were outside of this universe that were timeless and infinite. That is like almost as certain as you can get. And the mathematics in this universe is only a subset of the total possible mathematics that actually can exist and probably does somewhere. So whether you want to call that God, it's definitely something outside of this universe, that's for sure. Or ideal gas law. That's fun. Thank you, King Hor. I just figured out that's probably why you have 8 kids, which is awesome. We need more kids, man. That's so good. Is that part of string theory? It's deeper than string theory. Abstract mathematics is so deep that it's even greater than what is actually physically possible. Look up abelian matrices on Google. That will explain. If you look up abelian, A-B-E-L-I-A-N, abelian matrices, basically a subset of mathematics is called abelian mathematics. And abelian mathematics is what exists in this universe. So for example, 3 times 2 is 6, and 2 times 3 is also 6 in this universe, because both possibilities are mirror images of, so the mirror images of all problems have the same answer. Yeah. All right, so there are other mathematics, there are mathematics greater than the abelian subsets. It's called group theory if you want to look it up. But greater than abelian groups and abelian matrices is non-abelian. So you could have something where 3 times 2 is 6, but 2 times 3 is 5. So it doesn't match up. And in that universe, we could not exist. But that universe, at least in abstract, does exist. And it doesn't make sense that mathematics works perfectly and only a subset of it is in existence in this universe. So it makes more sense that there's a lot more of it outside of this universe that we can't see until we leave this universe. Anyway. All right, so E, dark matter. Yeah, I think maybe dark matter seeping in from outside. H, A. All right, so there we go. E is H, A. Now I think it's, I don't remember if it's H, A or H bar A. That's one straight universe, dark matter, dark energy. Dark matter is different. Dark matter is actual matter. So it's not like dark energy. They both have dark in them, but it's just because we don't know what they are. All right, so that means, without doing the full mathematics equations, V of X, which is the potential energy, right, equals 2 ma squared. It should be x squared. Yes, it is. Excellent. X squared. All right, so the potential energy of this particle, right, has 2. We must have some constant to get anywhere. Exactly. That's exactly right, yeah. V of X, the potential energy of X, this particle, is 2 times the mass times omega or A squared, and then the particle's location squared. Right? So you get all of that and you'll get its potential energy. So that's the new equation, right? So I'll put that there. I've skipped the proof because if I might do, it depends how many Patreon subscribers we'll get, but if I get enough that I can quit my job, then I'll be able to do other stuff like, I'll do like abstract mathematics and real analysis and group theory and stuff like that. Potential to kinetic. You could say that, yes. Kinetic energy doesn't completely translate in quantum, but if you see the last lecture I just did this morning or a few hours ago, you'll see the analogy. But yes, you're pretty close. I want more kids. Have my looks and your smarts. Imagine if they came out the opposite. I wonder if that'd still be cool. It'd still be cool. Okay. So now let's give you the standard deviation. All right, let's start with the variance. All right, has anyone done statistics? Because the variance, right, let's say, I'm just going to quickly draw this for you just so you can catch up. Let's say we have here a normal distribution, right? That means that the average location of the particle, right? This is the average here, right? Oh, you hated it? Stats and physics? Yeah, quantum mechanics is all about statistics, basically. So let's say that this is the average particle. The variance, right? We're going to call that, in physics we call that like that. All right. That here is the variance. It's not that difficult. I always say to people, if you don't understand statistics, then you just had a bad teacher. That's my rule. Average is still X. Okay? This average is the same as this average. But this one, let's just say this here is male IQ. This is actually true, by the way. Male IQ. Periscope. Damn it. And this is female IQ. All right. So this is actually documented stats, right? The average of female and male IQ is the same, X and X. But you've noticed for political correctness, I've pushed it up a little bit. Yay. Have tighter IQ. Tighter IQ, yes. Yes. So in other words, the variance here, okay? So up here, the variance equals, let's just say, 1 over a y, higher IQ. And here, the variance equals just y. What have I done? No, sorry, that's completely the opposite. That's y, and this is 1 over ay. Okay, so what does that mean? That means that there is more variance. That means that even though the male IQ is the same as the female IQ, there are more male geniuses and more knuckle-dragging men compared to women. Women will have less geniuses and less knuckle-dragging females. All right. Now, Jordan Peterson explains why this is the case, and he gives a very good explanation. So I would type in, if you want to know more about this, I would type in Jordan Peterson IQ, but I don't want to get to that here. The point is the variance. The variance is smaller here and larger here. What does that mean? What does that mean? What does it mean to have a smaller variance? What it means, that explains a lot. Sorry. Distribution, exactly. It means that the IQ distribution of females is more tightly knit. Diffusion, yes, also diffusion. The IQ of men is more diffused along the IQ spectrum. That's exactly right. So that means, back 15, watch the replay either way. All right, lovely to see you, Amy. Have a beautiful 15 minutes. All right. So that means if I'm looking for a male with average IQ, right? I'm studying, Dad, Mafiyu, sorry. If I'm looking for a male with average IQ, I have to look at a larger circle because the men are distributed further along, right? Whereas with the female, because the variance is lower, that means that I'm going to find a lot of them in a smaller, more confined space. All right, we're there. Excellent. So now I'm translating what I just explained into quantum mechanics. In quantum mechanics, if you're looking for a particle, if the variance is lower, then you don't have to look as far to get the greater chance of finding the particle. If it's a high variance, that means that the particle could be over here or way over there, right? That's what variance is. I think I've explained it okay. Fingers crossed. So thank you for your patience. Now, that's why females love selfies and are infatuated with makeup and the Kardashians. I don't see the connection, but I imagine some women and maybe some even men are obsessed with photos like that. All right, let's get back to variance. Here is this x squared, as I was saying. The equation for that is here, if you're ready. Okay? The equation is x squared. So this is not really x squared. I call it x squared, but it's the variance, right? That's called the variance. So the variance equals, sorry, let me give you the equation, right? The integral, it's so freaking hard with this delay, I tell you. I sort of have to close my eyes and just write. Integral of negative infinity to infinity of the particle's location squared. The particles are female. Well, some are male, some are female. How's that? All right. Psi squared dx. Psi squared dx. All right, which equals h bar over 4am. That looks hard. It looks hard, but once you do it a few times, it becomes really easy. So, are you just making shit up because no one would understand anyway? That's so true. I could be doing that. That's so funny. So, this here is the variance. As I said, this variance, right? Yeah, I would say go back and look at my past vids and to try and catch up a bit. But there's also some awesome videos on YouTube if you want. And there's a guy called Ben Garside, who is this gay English dude. He's so funny. He doesn't mean to be funny. He's just hilarious. He's like, now, as we go into the x squared, blah, blah, blah. It's so funny. He's awesome, but he's really, really good teacher. All right. So that's the variance. Is that trigonometry? Sort of. There's some trigonometry in it, but it's more calculus, which is sort of the next level up. But yeah, trig was invented by the Greeks 2,000 years ago. Calculus was invented only a few hundred years ago. Yeah. But it's just like a language, you know, like if you learn English, it's the same deal. It's not really that. It looks more scary than it is. All right, so we have the integral, which I explained earlier was the infinite sum from negative infinity to infinity. The location squared, the wave function, all right, that's the wave function squared, okay, which also equals h bar, which is the size of pixels in this universe, divided by 4 by the spin by mass. Is calculus relevant? Yeah. Without calculus, we wouldn't have mobile phones. You need these equations to calculate mobile phones. So basically, the inside mobile phones, the particles disappear into alternate universes and come back, and no one can see it, but we know from the mathematics that that's what's happening. And it's freaky that that's actually going on. And I mentioned this before a few scopes ago, where the radio stations are the same. You can use this second dimension of mathematics to split up the wave. Yeah, well, we don't know where it goes, but mathematically it goes to that other dimension and comes back, which is just, anyway, mind-blowing. So here is the equation for the variance. I took calculus and it kicked my ass, but I passed it with a C. All right, C for calculus. Well, listen, man, if you can pass calculus, then you're doing pretty damn well, because I don't know many people who can even pass it. That's funny. People just need a good teacher, honestly. All right, so now let's go to the probability density. All right. Probability density equals negative I H, right? So probability density, I spoke about this in the last 2 lectures on quantum mechanics, right? Probability density is the chance of finding the particle somewhere. That would be, I love the KFC logo. Failure is my teacher. That's good. I thought trig was more difficult than calculus. It can be. It can be very difficult when you're doing advanced trig, especially when you're doing like multi-dimensional trigonometry and polyhedrons and stuff up in group theory. That's pretty cool. Yeah, it turns out that the more testosterone you have, the better you tend to be at trigonometry, because it turns out testosterone gives the brain this ability to rotate things in its head. Yeah. So, okay. Moffat, thank you. All right, so to find the probability density, we're going to have IH bar, integral from minus infinity to infinity, of the wave function, and it's only the wave function, the spatial wave function, analytic geometry. Cool. And then we have the partial derivative, right, of the wave function. The reason it's partial is because it's only the spatial part of the wave function. If you remember, and understand so little, mate, you'll look back at this in a year and you'll be like, oh yeah, where is it? It's there. So that's the full wave function, right? And this is just the space wave section, because it's only got x in it. That's the time part because it's got t in it, right? So we're only using this part. So this part here, right, that's called, sorry. That's called lowercase psi, which looks like this. Right, it's the small one. And that one there is xt, that's just x. Okay. So coming back to it, we've got here the wave d, that should be dx. Is it dx? Yes, it is. So partial derivative x. All right, there it is. Dx equals 0. If anyone gets time, you should go back and do a maths degree. It's so much fun. I had a really good time. So this is the variance in the probability density squared. Right, these won't make sense yet, but this one's not going to make much sense, but once we do examples, it'll just click for most of you. All right, and it's not that difficult, because when you do an example, you're going to get you'll get everything in here except one thing, And you just have to solve it for that one thing, just like high school maths. It's not which university in Australia, Charles Sturt University online. I've been offered to skip my master's by doing a thesis, an honors thesis, and then which I'll probably do next year as long as the offer's still available. All right, so that equals negative h bar squared integral from minus infinity to infinity. All right. And once again, we have this, but now it's partial. It's now the second derivative. Let me just check I've done that right. Yep, dx, which equals h bar. Thank you very much, my friend. H bar ma. Okay. So, the next one is the standard deviation. Okay. So standard deviation and variance are related. Okay. Remember how I said variance here is big and here it's small? Huh? Right? So that's for the male IQ, that's for female IQ. Standard deviation is how far everyone deviates from the mean. Okay. So the standard deviation includes about 80%, roughly. It's like 86% or something, but it includes most of the population of men. All right, and here the standard deviation is really small, right? And that includes most of the population of women. So women are more tightly packed, when men are more spread apart. So here you've got the yeah, and then here you've got like the x squared equals right? With the women, they're more tightly packed. And one of the reasons is because women like men who were smarter than them in history anyway, and so they pick men who were smarter than them. But of course, the smarter women, there are less of them, and so there'll be even less smarter men, and they'll be way out here somewhere. Anyway, you can look at that at Jordan Peterson's site. That is not my specialty. Standard deviations. So I just explained what standard deviation was. Where did you figure this shit out? I am a weird bloke who basically is exercising right now as I'm talking to you. I'm doing maths and pedaling on my exercise bike. I didn't really answer your question. I don't really know. It's in my brain somewhere. Okay, so standard deviation of x, right? So this is now the particle, okay? Are Ortus numbers more male or female? More male by far. All right, so here we have x squared minus x squared. So here we go. This is going to be interesting. X squared, which is the variance, minus, which is that there is the average location. Okay. Okay. And that equals half of, we have h bar over the mass by the angular velocity, right? So that is the standard deviation. So what does that mean? That means that the standard deviation, right, if you remember, standard deviation is how much it deviates from the mean to find most of everything. So here, you're not going to deviate much from the mean and you'll get most women. With men, you have to deviate further from the mean. And that equation here, half of h bar over the mass by that just gives you the standard deviation. So when you do the actual questions, it's going to say to you, how does this differ from Heisenberg uncertainty principle? Two different things. Heisenberg uncertainty principle shows that you can't get both the location and the momentum. You can only be accurate about one of them and not the other. And there's a really good reason for that. And if you listen to my last lecture, I talk about the traffic light theory. I was just talking about traffic lights. And if you think that quantum particles are like the traffic light moving from green to red, then it will make more sense. All right, 2 out of 9, 1 out of 9, that's done. Now where is 3 out of 9? I think I've lost my page. There it is. Okay, I'm actually about to talk about the uncertainty principle, so well done. Okay, excuse me. Alrighty, let's go. So, the standard deviation of the probability, right? This is now the probability standard deviation, equals h bar ma square root. All right? And the uncertainty principle Here's the uncertainty principle. It is the standard deviation of 1 changing and moving. Good question. In quantum mechanics, yes, because it looks like it's moving, but it's not really. Just like, you know, the traffic lights, like traffic light. If you're going from green to red, in our brains, we just treat it as if the light is moving, excluding time. This would include time. What was I going to say? It looks like the light is moving, but it's not. One turned off, the other one turned on. And our brain treats it as if the light is moving, which is what's happening in quantum mechanics. There's an illusion of movement because the particle appears and then disappears, appears somewhere else. All right, so this standard deviation multiplied by this standard deviation equals h bar over 2, right? Within space and time or absence of time. I'm ignoring time at the moment to show you the uncertainty principle, but it'll be the same thing. Once I add time, it's the same answer. Okay, so when that by that equals that, that's the smallest amount of uncertainty you can get. Why is it? I'll tell you why. Because when you think of the traffic light, right, you think that, you know, that's awesome. You think that, for example, there's a green light and then it becomes orange and then it becomes red, but it doesn't move in between, right? So think about it. Where is the light in between when it goes from green to orange to red? More space is less time. It could be, yeah. Sometimes it could be, yeah. So green to orange to red, there's no gap. Have you noticed? Like it doesn't go through the gap. It sort of appears, disappears. It doesn't exist. Right? So that's why you have the uncertainty principle. Yeah. Because you could pick a time where there is no light on, because the one light disappears and goes to the next. There's that little infinite amount of time in between where the particle doesn't exist. And so, like, you know, at the traffic light, the light is actually off outside Newtonian physics. Absolutely, that's exactly right. So, for example, someone could try this, right? Maybe next time you're at a traffic light, hopefully not in your car if you're walking or something, when it's going green, when it's about to go orange, or if you're going from orange to red, take a photo or take heaps of photos, and one of those photos will show the light with no lights on. It'll be completely blank. And then say to yourself, where's the particle? So it doesn't exist. Where is it? Right? Because it's between pixels. And that's why there's an uncertainty principle, because you don't know where it is. If at certain times you might know its location, you don't know its speed. So it complicates standard physics. Yeah, standard physics, chuck it out the window with quantum mechanics. You can know its speed, it blinks out of existence. That's right. Illusions. That's right. It is an illusion. That's exactly right. Exactly right. So anyway, let's move on to the next equation. Because here's the thing, if you take a photo of the traffic light and it's all blank, right? You know that the light is moving because it was green or was orange and it's now going to become red or something like that. It's clearly in a state of transition. But if you take a photo of it when the light's on, you can see where the light is, but you don't know how fast it's moving. So it's one or the other, right? That's basically what's happening in quantum mechanics. Charles Sturt University, my friend. Buddy, you must be Australian. I feel smart right now. You are smart, my friend. That's why you're here. All right, where's the next paper? 3 out of 9. 4 out of 9. Here we go. Okay, these are just people asking questions, so I'll skip that. Now I want 5 out of 9. Here it is. Excuse me. 5 out of 9. Oh, that's all wrong. Where's 6 out of 9? 8 out of 9. Where the hell's 6 out of 9? What's going on? Bloody hell. Frickin' shit. Where's everything? That's 7 out of 9. 9 out of 9. Thank you for wasting my time. 3 out of 4, 2 out of 4. All right, here we go. Sorry, just woke up from a dream and arrived here. I hope it wasn't a bad dream. 1 out of 4. Here we go. Okay. Now, we're going to look at the time section. Okay, this is the time-independent Schrodinger equation can be separated into two things. And then we solve for the time component where c is a constant of integration. All right, cool. So let's now do the original Schrodinger equation again. Let's go. I'm just going to show you another version of it. Why is this not? Come on, man. Ah. Freaking. There we go. Well, actually, just a comment on Sol. It not only does the particle disappear, but time disappears. That's weird, right? Time disappears as well. So at that level, we're not going through time. We just skip from one fraction of the second, you can call it a Planck of a second, to the next Planck of a second. We're like photos in a frame. Yeah. We are like, if you get photos and flip them really quickly, we look like we're moving, but we're not really. We're snapshots of different things. Yeah, that's right. Faster than light. It's at the speed of causality itself, which is basically time equals 0. Yeah. All right, so let's have a look at the next equation. Okay. Now I'm going to show you the more generic version of the equation. So minus h bar squared over 2m. Sorry. Man, this is so freaking annoying. H bar squared over 2m. Picking up the phone. Man, you guys got to put your phone on silent when you go to sleep. That's what I do. Otherwise, you'll never get any sleep. D squared psi. It should be a partial. Dx squared. This is better than YouTube. Well, I put these on YouTube at the end as well. Mute always here. All right, so plus v of x, right? Psi. This is the full psi of xt, the full wave equation, plus, so this could actually make time traveling possible. Oh, time traveling already happens. The satellites that are above us for our mobile phones, they travel closer to flat time, where we go into their future already. Plus, you're talking about quantum entanglement. Yes, that travels faster than light. But it's not actually traveling as far as we know. All right, equals I h bar partial derivative of that with respect to time. All right, all I've done now is that's h bar, which is the pixel size of the world, called the Planck's constant, divided by 2 pi, squared over 2 times the mass, second derivative of the spatial section of the wave equation, so the space component, second derivative, plus the potential energy multiplied by the full wave equation, plus a constant. Why is that important? This constant's important because you don't know where you're starting from, right? And I'll explain that in a moment. I by h d, the time component of the Schrodinger equation with respect to time. So that's like the speed, I guess, the average velocity of the particle, right? Multiplied by complex number h bar. Where am I? Just make sure that I haven't made a mistake. No, that's all good. All right, because the minus is over here. Perfect. All right. So the average velocity multiplied by the pixel size and the complex number, right? Because that means it's in another dimension, right? Equals potential energy by the wave, second derivative, and h bar and 2 by the mass. What if is this shit? It's the shit that creates mobile phones. Without it, we wouldn't have them. All right, and V naught, which is the initial potential energy. Now, why do I say that? Because imagine here is a cliff, and here is 4 hours and no audio notifications, so can't blame phone. Yeah, but once you look at it, you wake up. Right? So here is, I don't know, someone from here, and that's them, right? Hey, I wish I was smart enough to understand this. Ah, you probably are. You just app developer? Me? Nah. Damn, so people that know how to do this shit. Damn, so people know how to do this shit. How does it relate to quantum entanglement? It does not yet. I haven't brought that up yet. But basically, quantum entanglement is part of this wave equation because this wave equation actually gives two answers. And one of the answers is the mirror image of the other. And that mirror image is what we're looking at as either the antiparticle or quantum entanglement. So let's say that Nellie Bell throws a rock off a cliff. Now, let's say she holds it and then she just drops it. So, right? Slit experiment. Yeah. So this here, right? She's holding a mobile phone. Okay, and she chucks it off the cliff. Engineering course in college. Awesome. Welcome back. All right. All right. So she throws that off. This particle, right, has a potential energy already. Right? All right. All right. So because it's up on top of the cliff. More sounds, please. Raggy? Referee? This summer, Nellie Bell throws her phone off the building. All right. So she drops it off. It already has potential energy because when she drops it, right, she doesn't have to, she doesn't have to actually throw it. She just has to drop it and gravity does the work because it already has potential energy. And so therefore the potential energy is not zero, which means it's V naught. And that is the V naught here in the equation. So maybe this equation represents a particle that's already moving, for example, or already falling or whatever. So that's why we add this component. That's pretty much it. That's the mathematics of that component. Applying separation of variables, now we can get the energy, which is pretty damn awesome. And we get this. I'm going to skip the actual complex mathematics. I would entangle the ball with another ball and play with them. That's not a bad idea. Gravitational pull, exactly, absolutely. And as we now know, gravity is an illusion. It's the bending of space-time, and it looks to us like gravity, which is pretty awesome. Otherwise, light would not be bent. Okay, so E of t, so the energy is a function of time, equals C. And the reason I have the C, or it looks like a G, right? It's a C, right? C represents the V naught. When you integrate the V naught, the potential, right, you're going to get a C, right? Which is just some number that we don't know yet. Okay? Now, where's my magnifying glass? What about time travel? Time travel happens all the time for massless particles. Okay. E, I wish my money was entangled with my wallet. That's the best joke of the lecture. E to the minus complex number I. Energy plus V naught. You're a better teacher than my algebra teacher was. Awesome. Energy plus V naught. T over H bar. T over H bar. All right. It was very good. All right. So here we go. So now we want energy as a function of time. And what does that mean? That means that we can figure out the fluctuation in energy of this particle if we know C, and we can just plug in any time we want, like 3 seconds, 5 seconds, whatever. We've got H bar, which is the size of the pixels of this universe. We've got potential energy plus the energy, right? So that's potential energy, and then energy as it falls. I have more energy. Simba, remember. Right? And then we know E is a magic number, and I is a complex number. So we chuck them all together. If we have the time, we will get the energy at that time, which is pretty awesome. So that's the other equation that we will be using in this course. Okay. What I'm doing is I'm just reading the lecture notes and then teaching, and the finite math one too. As always, my friends. So, the phase factor disappears when calculating any physical quantity, which is pretty damn amazing. So, let us move on. We now have the equation. 2 out of 4. All right, let me find the next one. 3 out of 4 is just people asking questions. Okay, now all my papers are backwards because they got blown by the wind, of course. They got blown. All right. Now, a time-independent case. We've already done this. First, since the energy is feasible, we would expect that to be a real number. This is easy. That's fine. All right, here we go. The next one. And lucky I bought these books from a lady that went bankrupt. They were so cheap. They were like, no air friction. At the quantum level, no. But we do have relativity, which does mess with things as we will move on in this course. So, next, we have another version of the equation. We have d. Why is my finger shaking like that? That's weird. All right, d squared phi, I always confuse them, dx squared. All right, that's not squared. I always call it squared, but that's a derivative. That's the second derivative of psi with respect to x. Oh, you can see my legs pedaling. It's funny. All right, equals, I've done at the moment 150 calories, which is pretty awesome. All right, that equals 2 by the mass over reduced Planck's constant squared, right? And then we've got the potential energy V minus E, which is the actual energy. So we want the energy difference, right? Right? Of lowercase psi. That's it. So there you go. This is the spatial version of the equation. This is time independent. So we could, if we had X, right, and we had the equation for psi, and we had the mass, we could find out the difference here. Math hurts your brain. Impressive. Oh, thank you. Okay. So, if this is less than this, right? In other words, if the energy is less than the potential energy, right, then we know that that minus that is always going to be greater than 0. Now, what does that mean? That comes back to, remember the lady on the cliff? Now it's another cliff, and now we got Big Worm on this cliff, and he's like, yo, I'm going to throw this over back. Right? So what happens here is that you can see that the potential energy is greater than the actual energy. Because if you let go, it's going to fall. It's going to fall down. So clearly, right, you got here some potential energy which is greater, and that's what's happening here. If that is bigger than that, then this is where you are in real life. All right, that's what's going on. Yes, it's very confusing, isn't it? That's what happens in quantum mechanics, and that means that the particle won't exist. I'm going to get into that as we move on, right? Let me move on to the next thing. All right. Yeah, it's pretty crazy. So this here is when you have a well, let's just say. Now here is the wave function. Now inside the well it gets trapped. In here, when it gets trapped, that's when you see a particle. So you're going to see a particle, and at the moment we're only doing this type of well. So the particle's bouncing left and forward, right? So here we can see that there's an actual particle. But on these sides, we're going to get no particle. We're just going to get a wave. And this will happen when we solve equations later on. If the potential is even, then it can be taken as even or odd. Okay. Replace with negative x. Okay, now we're going to talk about Ehrenfest's theorem. Okay. Yeah. You know, I just read these lecture notes, so I'm only one lecture ahead of you guys. All right, the expectation values, means or averages of observable quantities in quantum mechanics obey classical laws. All right, so this is interesting. Has anyone seen those cloud things where you see particles? At my scholarship, I was able to see actual atoms in this awesome microscope that they had before I was kicked out. Alrighty, so the expectation values, so the averages, actually work like real particles. So that's another weird thing. So, you know, with quantum particles, you can't find one particle, but if you use the average TEM microscope, it was some sort of back. What do you call it? It's like some sort of electron or positron reflection microscope or something where it like disturbed the particles. It was pretty crazy. And then they get recreated mathematically. Backscattering, that's the one. You know your stuff. Yeah, that's the one. What's interesting is that the individual particles in quantum mechanics, right, you don't always know where they are. But if you get the averages work as if it's a real particle, which is unbelievably weird. So we are all made up of average amount of particles, not actual particles. Right? So, you know, all of you guys and me and the phones and everything, the particles that make up all of us come in and out of existence and disappear and go wherever. But we as a collective stay the same. So it's sort of like, imagine you have a house made of bricks. Something is taking bricks in and out, here and not here, yeah. So the bricks are always getting replaced all the time, but the house is still there. So what really is the house? Hello, welcome back, Miss Arizona. Nice to see you. What is the house that you're living in if the bricks keep getting replaced every second? So you wake up the next day, it's still the same house, but they're different bricks. Actually, that's weird. Or maybe one brick at the bottom is now at the top, right? They keep moving and moving and moving all the time. That would be so weird. That's what's going on, right? But we think we're just the same thing. So really, what are we? We're information, I guess, more than actual real people. Very bizarre, right? You like analogies. I don't know if I like analogies or analogies like me. I'm not sure. And the bricks all the same size. Yes, all the same size. Ehrenfest Theorem. That's right. Supernova. Bingo. I remember you from before. You love analgesic. This goes beyond biological shedding. Yeah, that's right. That's so true, right? Crazy. All right. So based upon that, we can look up the average quantum momentum. And I'm going to show that to you now. Hola, that's a bot. See you later. All right, here is the average quantum momentum, which I'm going to draw for you in the form of a rho. All right. My sleepy typo finger. No, that's okay. You can use your awake typo finger next time. All right, equals negative I h bar integral of the full wave function psi, and it's the conjugate, all right? Complex conjugate, and which we talked about at the beginning of this lecture and plus the other lectures as well. And then we have partial derivative of psi with respect to x. So this is only the spatial section of the wave function, right? This is the spatial section of the wave function, and we want the derivative. So that's like the speed, in a way. You could sort of call it that. It's not really, but in your head, it's the easiest way to understand it, right? So now that's the formula for momentum. Because of Ehrenfest Theorem, we can use this version of momentum, because basically we have mass by velocity. All right? There it is. All right, there we go. Now, eventually you must teach stand-up comedy too. That's funny. Now, what I'm going to do from now on, and this is, if anyone's done sort of, advanced calculus at university, what we do is we change these. So to make it easier, right, what we say is quantify me all day long. That is terrible. we can talk about square roots. That's so bad, right? Is going to equal that x. Okay, I'm just changing the notation, right? And so therefore, the next derivative, so derivative of that, which will be d2 phi dx squared, right? That's the second derivative, is this x, right? So that is that is that. That's just notation, right? It just makes it easier once we do heaps and heaps of equations later on. Okay. Now, so we have the momentum formula. After we get all these formulae, then we start doing some questions later on. Okay. So now, d rho dt. In other words, the change in average momentum over time. And remember, the average values work as classical values using Ehrenfest Theorem, if you remember, right? So d row your boat over time, 10-4, equals, right, the average of this. Okay. There it is. So this is the derivative of the potential energy with respect to x. Okay. And all we're doing, I'll show you what we're doing here. So that's d rho dt is negative that dt. Now this is actually because we have a harmonic function. All right, so what's interesting, harmonic functions, let me talk to you about them. In mathematics, they teach you harmonic functions. Harmonic functions, you got all the momentum I need. Man, isn't your husband going to go crazy if he sees your messages? Oh, that's funny. I'm actually burning calories as we're doing it. I've done now 183 calories as we're talking. You can see here I'm pedaling. You can on my exercise bike. All right. Nah, you're invited. Awesome. It's good to know when I'm at Arizona. Oh, my dear, you're terrible. You got a cheeky smile. Harmonic function. Yes, supernova 3, correct. Supernova 3 has a lot of experience in physics. That's my impression of you. I'm eating food at 3 a.m. Eat some food, why not? I just had a spinach salad. It was amazing. Hello, that's another bot. See you later. All right, harmonic functions. Harmonic functions are a subset of functions. Now, harmonic functions are the ones that exist in this universe. But non-harmonic functions exist in mathematics. They just don't exist in this universe. That's the weird thing. Very weird. So if you try to map a wave equation using a non-harmonic function, the electron will never exist. So it's like, for example, the traffic lights. Imagine the traffic light was created by humans, right? And it was created in such a way that you can only have green, orange, and red. You can't have a light in between, right? It's forbidden. And this universe is the same in that respect. I hope you function. That was unexpected and very witty. Oh, God. Oscillatory motion, my dear. Too funny. Now, I'm going to show you what I mean. Have a look at this. Okay. Here is a three-dimensional function, right? This is one dimension, and then this is the 3D version. It goes like that, and like that, and like that, over there, right? So, an intelligent scoper. Oh, wow. So, here is the waves this way, and there's the waves that way, right? So, that's three-dimensional. Okay. Now, what happens in this universe is that when you take the slope this way, right, you can also take the slope the other way. Now that means, right, that you can't have this. You can't have a mountain that just goes like that. This does not exist in our universe, right? You can't just magically appear up there. You have to connect the dot. Okay? I'll show you another example. Right? You can't have, here is a stair, right? This is now steps. Okay. You can't get back up here okay. How can I draw this? I'm not an artist, as you've noticed, so I can't draw this. Let's see if this works. All right, this is sort of what I'm trying to say. If you step down from here and walk around, your brain automatically tells you that you're walking uphill to get back to the top, to step down. Up the hill, step down. Up the hill, step down. You cannot step down and then step down again and then end up back up here. All right? So what that means is that in this universe, E equals mc squared. Yeah, not too bad. Good try. You can't go to the next floor unless you go up there, right? And to come back down, to get back again, you have to go back up. But mathematics teaches us that I'd climb any hill for you, darling. Really? Get your Australian passport. I'll see you soon. Very funny. You cannot keep going down steps and then end up back at the top. You have to climb back up to get to the top again, right? So life is not a never-ending water slide. That would be pretty cool. I'll slide anywhere for you, darling. I was waiting for that. But mathematics teaches us that in other universes that can be possible, right? But whether those universes actually exist, we don't know. But it's definitely not possible in this universe. Anyway, so the way for that to occur is this. I'm going to show you in mathematics what that means. If I have a function, right? The function is u of xy. Like that movie Inception. Exactly like in Inception. That's exactly right. U of xy, right? Now, if, right? If it is a harmonic function, right? Then, right? When I get the slope of this, right? I'm going to get the slope in the x direction, right? So as I showed you here, this might be the x direction and the other way might be the y direction, right? So I'm going to get the slope here. So u of x, right? Which implies ux x, which is the slope of the slope, equals u y y equals 0. Right? So this is what should be happening. In other words, the slope in both directions equal each other, which means that we don't have the inception type of staircase. So we have normal staircases in this universe, but mathematics shows us that there are step cases that look like inception that do exist, but not in this universe. We don't know where they are. Uxx, uyy equals 0. Yeah, exactly. So the slope of the slope, right? And that's what you'll get with your harmonic function. All right, next. 5 out of 6 is just people asking comments. All right, here we go. Let's do some statistics. It's amazing. Equals uyy equals 0. That's the one. You got it. All right, so some statistics. I'm just going to show you this because it's heaps easier. So the first 25 digits of pi. Okay, so if anyone knows pi, pi is the ratio between the diameter of a circle and its circumference, which is insane. So the Greeks discovered this 2,000 years ago, even more. They discovered that doesn't matter how big or how small the circle is, the circumference close to 22 and 7. Yes, very close. Well done. The relationship between the diameter and the circumference of the circle It's always the same. And the thing about pi, because it's a transcendental number, because it's always pi, damn straight, because the number goes on for infinity, it shows you that there is no possible true circle in this universe. And why is that? Because this universe is pixelated. Cherry pie. No jokes about popping cherry pies. Oh, God. All right. So, let's go to it. Okay, so, here, so basically, to get a true circle, right, I'll show you. A true circle, right, no true circles, that's right, and that's more evidence to show that we're living in a pixelated universe, because that means that if you zoom out down far enough, you're going to get little squares of pixels. Exactly, with infinite number of sides of a circle. Is this how 360 scope works? It's funny, but that is actually how it works, where it translates a rough estimate of circles using algorithms that represent them in the form of pixels. Yeah. So we are living in some sort of illusion, right? This idea of a 3D world. Yes, 3.14, 159, 2653, 589, 793, 238, 46, 2643. Yeah. Alrighty. So what he's done, the frequency of each digit and the probability of getting each one are. Here we go. Have a look at this. Okay. So out of all of those numbers, all right. So that's the number, right? 1 shows up 2 times. So if you look up here, 1 shows up 2 times. 3.141. So 1 shows up 2 times. All right. 2 shows up 3 times. 3, 5, 4, 3, 7, 1, 8. So the one that shows up the most is 3. There's 5 of them. So the chance of that number showing up is 0.12, which is the highest. But 9 can also show up. That's also bizarre. Oh, no, that's 0.2. Yeah, 0.2 is the biggest one. So you have a 20% chance of finding the number 3. There's a 20% chance of finding number 3 in pi up to the first 25 digits. All right. The most probable digit is 3, because you have a 20% chance. The next nearest ones have a 12% chance. Okay? The median is 4. The median is the middle number. The median is the middle number. All right? It doesn't mean it's the average. It means it's the middle. Okay? And the average is 4.72. The average is 4.72, which means that the numbers are skewed more to one side than the other, which is very interesting. All right, we can get the variance. All right, the variance is 6.1216, so the standard deviation is 2.474. All right, what does that mean? Well, this comes back to what I said before. All right, remember the variance? Who remembers variance and standard deviation? I'll show you. I was using male and female IQ, right? So here, male IQ has a much larger standard deviation, right? Good memory. Much larger standard deviation because there are more dumb men and more genius men. Whereas with women, even though the average IQ is the same, they have a smaller standard deviation because women are more tightly packed. You don't have anywhere near as many dumb women or as many female geniuses. And that's exactly expected because standard deviation, you got it. Excellent. Good. So that's how physics works. Okay, the next one, I didn't get through what I wanted to get through, man. Pretty shitty about that. We've gone through half of what I wanted to get through. Median is 4, average is 4.72, variance, standard deviation. Standard deviation was 2.1. 2.474, and the variance is simply the square of that. The theory of everything, yeah. So the square of the standard deviation is 6.1216, which is just the square of 2.474. I heard about only mean and median mode. Yes, that's how it starts. And then as you get into like high-level physics, high-level statistics, you do those ones. Yeah. But basically everything is like that. Might have to go chat-free for some of it. Yeah. The problem is what I'm going to do another scope now just to fly through it. I think that's what I'll do. And basically, are you a PhD scholar? Almost, yes. I've been offered the opportunity to skip my master's after topping the uni, which I got really lucky with. So yeah. Alrighty. I'm not sure. What do you guys think? Do you think I should do another scope and just do one that's like pure maths and fly through the rest of this? It might be a bit harder to follow. That's the only problem. But it's up to you. It's up to you what you guys want. More review is always good. I would say, yeah, it's faster. Okay, that's one. Yes. Teach me good. Okay, I'll take that as 2.5 yeses. Do what is best for you. That's a good idea, actually. That's good advice. Separate to we can find it later. Okay. All right, I'm going to do that. I'll see you guys later in a couple of minutes. If you're into maths, let's get into theoretical physics. All right, let's do that then. I'm going to bed. Sleep well, little Bill. Lovely to see you guys. And the rest of you crazy mathematicians, we'll see you very shortly.